Right, good morning, guys. Welcome back. So, leaving or starting off where we left off yesterday, we're still doing normal distribution, still doing hypothesis testing. Hopefully finishing all of that today. And main focus for today is to get you guys used to deciding what kind of distribution is this. So you'll get given a question, and we're going to try and work out what you're supposed to do. Is it asking for me to do a normal distribution, binomial distribution, by hypothesis testing? Am I approximating a binomial? So really trying to work out how to kind of read a question. All right. Could you guys comment when you're here? There's a few of you here at the moment. So let's just do some register. So you've got Frank, we've got Joseph, Regan. Sam says 11. Not. I will change that later. Oh wait, no, I can change that right now. Thank you, Samuel. 9:15. I don't know why that's in caps either. Cool. All right. Where are we at? Sam Humphries, nice one, Dan. Went to the wrong room. Cool. Anybody else there? That's five of yous. Wait, no, it's not six. Sam Humphries, no. Sam Humphries, Sam Stevens. Yes, cool, six. Yep, it says there's only six of you. That's poor turnout, everybody. All right, so we're going to start with this question, which we didn't quite get round to yesterday. So we've got a sugar machine, and it's filling packets of sugar. The weight of sugar delivered to each packet can be normally distributed. Manufacturer requires that the mean of the contents in each packet is 1010 grams. And 95% of all packets contain between 1000 and 1020. So there's two criteria here to meet. First of all, we've got test. We've got a test there for the means, and also we've got to make sure that we're in the right amount for our majority of the data there. Okay, show this is equivalent to demanding that the variance is 26.03. So we need to find the variance first of all. Cool, so that's going to be using a Z distribution. So that's the standard normal. Let's put Z as well. Then we've got a sample of 8 packets selected at random from those filled by the machine. Those are the weights. Assuming the variance is what they said just now, test the 2% significance level, whether condition 1 is met by the machine. So then we got a normal hypothesis test. Alright, so 7 marks. Let's get this as our starter so you guys can wake up a bit. So 7 minutes starting from now. Give it a go. Comment your answers when you've done it. Cool. Hannah Casper said I will take you guys off if you get started on the question. All right, let's try and get through this. I keep doing that. Make sure you're commenting answers, please, guys, or I have no idea what you're doing if you're stuck or any of that. So please make sure you're putting your answers or any questions you got, and I'll answer them as we go. Has anybody else arrived? Because I'm still only got 9. There's only 10 of you here. Dan normally does it twice, so that might be it actually. Right. Anyway, let's get started then. So, right. Normally distributed. Okay. So we're trying to find the variance, and we know that the mean has to be 1010. And we know that 95% is between 1000 and 1020. There's an easy way and a hard way of doing this one. The super easy way is to go on 95%, and remember back to the other lecture, that's mu plus 2 sigma, and then just work it out like that. I'm going to do the other way because I think most of you forget that, but you could just say mu plus is what we're dealing with. So mu plus 2 sigma equals 1020, and do it like that. Put mu in, and just work it out. So we'll check it with that in a minute. So the other way is to use a Z distribution. So we're going to find Z for when the probability is 0.025, and then code Z and use it to find the mean. So on our calculators, ooh, what have I done here? If we go to Invna, move this down. Geometry, don't know what I was doing there. Cool. Dist norm Invna. We'll go for the left because I think that's what everybody can do. Left, please. And 0.025 is what we want this time. Sigma 20, no, don't know sigma. So sigma is going to be 1 for our standard normal, and mu is going to be 0 for our standard normal. Execute. You get Z is minus 1.96. Okay, so we're going to say Z equals X minus mu over sigma. So minus 1.96 equals X, well that was 1000, minus mu, which is 1010 over sigma, and then work this out. So we'll do and we'll get 5.1 as our sigma. Cool. And we can kind of check this out as well. I think it's going to be slightly, I reckon we'll get sigma as 5 if we do it the other way. So if we do it the other way, 1020 take 1010 equals 2 sigma divided by 2, yeah. So 5 or 5.1 would both be acceptable answers for this one. Okay, all right, I'm going to write down sigma. Oh, wait, sigma, oh, the variance it wanted, didn't it? So we need to square that. And I don't think I'm going to be very accurate. We get 20, oh no, 26.1, yeah, maybe I should have used more points there for Z's. All right, let's do that better. I didn't really read the question. So Z was 1.9599. Oh, 1 point. This is stupid. 1.959964 is as much as the calculator gives me. So we'll divide minus 10 divided by 0.9599964. Get 5.102, square that. Yeah, now you get 26.03. Yeah, so yeah, that's a bit tight, I think. But yeah, so sigma should be 5.1021. That should work now. So get that, square it, and we get 26.03 for our variance. Cool. Okay, let's do the same. Well, let's do the next one. Hopefully no one's got any questions about that. It wasn't too bad. Oh, okay. Next one then is saying we got a sample of 8, and those are the weights of our things. Assuming the variance is that. Okay, so we're testing at the 2% level whether this sample concludes that it's different. So we need to do our sample mean test. The states are null and alternative. So H0 is that mu is, what was mu again? 1010. H1 yeah, so mu is just different to it. Because just the condition we need to fulfill is that the weight is that. So if it's not fulfilling that, the weight is not that. Could be more, could be less. Okay, so our mean distribution, if we use let's use W for the weights. So the mean distribution of weights is a normal with mu as 1010 and the variance as 26.03 divided by 1, 2, 3, 4, 5, 6, 7, 8. Okay, I haven't written squared because that's 26.03 is the variance, not the standard deviation. So it already is sigma squared. Okay, so we're trying to find to the 2% level. So we're looking at 1% for each tail. 0.01. 0.01. So I can bring those up on the calculator. We can find our critical regions. So if we do left first, area 0.01, sigma is going to be the square root of, let's put this all in actually, because the whole thing is the variance, so 26.03 over 8 in brackets, so we're making sure we square root the whole thing. And mu was 1010. All right, execute. So my lower value, 1005.8. So let's say W less than 1005.8. And for the upper one, let's just change the tail. And we get 1014.2. So W is more than. Cool. So those are my critical regions. All right, last we need to do is actually find our test statistic. So we got all these values. We need to actually find what the mean from our sample is. So we're going to go back to the calculator. I think it's units squared. I think it's the units squared. What do you mean there, Frank? Yeah, it is the unit squared. Yeah. Oh, okay. Cool. Yeah. Yeah. You guys have sorted out your own questions there. All right. We need to work out the mean of the data. So I'm going to type it all into the calculator. 1.1012.6, 1017.7, 1015.7, 1020.9, 105.7, and the last two 1009.9 and 1011.4. Type all those in. We need to do setup again on this. So calc set frequency is 1. Yep, good. We're going to do one variable analysis. So our mean is 1013.4. Cool. Is that critical? It looks like it's not. It's close, but it doesn't look like a critical value. So we can say there is evidence to suggest the machine is fulfilling condition 1. So not critical, except H0, evidence, some machine is fulfilling condition. I can't write down here, condition I. You can't see it anyway. That just says except H0, there is evidence that the machine is fulfilling condition 1. Right, anyone got any questions about this? Why can't the H1 be more than? Because it doesn't say that. We're trying to test if it's different. They would always say, I mean, you can look at the samples, yeah, they do all look more than. I mean, not all of them. There's a 5 there, there's a 9 there, there's 2 that's less, so uh, you can't assume it from the data, you have to assume it from their test. If the factory says, we want to be 2% significant that the machine is not broken, you can't say, well, I think it might be broken this way. You gotta do it the same every time. All right. So moving onwards, I think that's it for that. Yeah, for that set of questions. So I'm just gonna clear this one and get it ready for my next class. Cool. I'll just leave this one. Give me 2 seconds. No, still not left. There we go. Right. So we are doing. Which one is it? Nope. 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 Maybe this one. Yeah. Okay. Nope. This isn't right, is it? Where is it? Oh, I must have named it wrong. No. This is worrying. Have I not saved my slide for this one? A2A1. Oh, okay. Sorry, it's this one here. All right, yeah. So what sort of distribution is it? Sorry, guys, can find it there. So I just thought we'd talk about some ways you can detect, because when you see me doing it, I just kind of tell you guys, oh, it's this, this, and this. You need to be able to do that for yourselves. So first, how do you know what kind of distribution is it? Well, a binomial distribution should have a number of trials. Okay, so it should be clear. But if you're doing a normal hypothesis test, or if you're talking about the normal sample means, you will also have a number of means. So the point is, yeah, there might be a number in both. In the binomial, it's going to be a number of trials, so it will just be like 5, someone buys 5 things. if the normal distribution is having a number, it'll be they buy 5 things and the mean of them is this, or they buy 5 things, here's their values. So the binomial is concerned with how many of something do something. The normal is concerned with the mean of the number of things. So this one's always to do with number. This one's to do with an actual variable. So it might be mass, might be length, might be size, might be temperature. There's a variable, an actual number that changes, and we're trying to find the mean of something to do with those numbers. Binomial, 5 of them, 10 of them, 20 of them. There's no actual, it's a number, it's not an actual value. So it wouldn't have units in a binomial. Okay, and in binomial, you've got trials relating to a fixed probability. So each of those trials has a probability of being true. Whereas normal, if you've got trials, they're just numbers. Binomial have words like at least or at most or something like that, so you know that you're doing less than or equal to or inclusive ones. And binomials do have a number of successes or a number of items. That's it. It's always a number. Okay, with the normal, you'll have your mean there, which standard deviation there. If you've got any of those, it's probably a normal distribution. Um, and as I said, it normally links to the size of the variable. So it's about measuring an actual value. It's the probability of the value of a variable. So hopefully that clears it up a little bit. Both might have number. This one's a value, an actual, it means something, and this one is just a count of an item. So item counting, values. And this is why this is all about the mean. This is all about the number and the probability. Okay. All right, how do you know when to use Z? So how do you know when it's going to be a Z distribution with sigma is 1 and mu is 0? Or when, so we use it when we're told mu is 0 or sigma is 1, or when we're trying to find mu and sigma. So if you don't know mu and sigma, the only way to find them is to use a Z standard normal distribution. There's a few other times you might, so you could always use it for hypothesis test if you wanted to as like an intermediate. You could do everything with Z and always kind of turn it back into X values, but often it's easier to use X on the calculator, but you have to use Z when you're trying to find the mean or when you're trying to find the standard deviation. Okay, when to use normal approximation to binomial. The only real surefire way is it will say use a suitable approximation. So if they say that, the only approximation you guys know is the normal approximation to binomial. So that's a clue to use the normal approximation there. Yeah, so that's roughly how you know when to do different things, and you just kind of get a feel for some questions as well. Cool. All right. So for the rest of the lecture, we're just going to look through a load of different questions, and then we're kind of done with this. And then after Easter, we just got 1 week, smash through the last topic, and then we've finished. Yeah. Okay. So we're going to try some of these. I thought we'd start off easy. This one's only worth 4 marks, so it's not too tricky. I'm just going to move it down slightly there. All right. Yeah, so give it a go. I would really like some comments in the answers because at the moment it's kind of just me talking. So please give this a go as well. 4 marks. I will give you guys 4 minutes. I don't think this one's too bad. I thought we'd start somewhere pretty straightforward. So give this a go.
Use 12. Yeah, you give them 12. 12's the thing you're testing. So is it less than 12? So we're assuming the mean was 12. You only need to work out the mean if it's not given to you. So we've been given two things. The mean the sample is 11.1. That's what we're testing. We're testing whether the mean temperatures, so the whole population, is 12. Ah, yeah. Dan asked if the mean was, how do you know it's 12, or do we work out something else? And the way we do it is reading through. So the mean of the sample is 11.1, so that's the thing we're testing, and we're testing that against 12. So 12 is the population mean. So writing out, we got a standard deviation of 2.3. So 2.3 squared over 20, which is n. H0, we're saying mu is 12, and H1, saying mu is less than 12. Yeah, nice one, Sam. So do a sketch. We've got 5%, so we're looking for this critical value here. So bring back the calculator, back to distribution, norm, infinite, tail to the left, area 0.05, sigma, what am I doing? 10. Sigma is 2.3 over root 20, and mu is 12. Cool. So Sam reckons 11.15, and I agree. Which is here. Cool. Okay, so what do we get? 11.1. Ooh, okay. So 11.1 is looking pretty critical. Yeah, so 11.1 is less than 11.15, therefore critical. So because it's critical, we're going to reject or accept H1. The daily mean is less than 12. Cool. All right, everyone okay with that? These should be becoming pretty straightforward now. We've done a fair few of these questions. Right, on to the next one. Rattlesnakes. Cool. This is a fun question. Love this one. How can we use 0.05? Because Dan, it's a one-tailed test because it just says it's less than 12. So we're only looking for one tail. So we don't divide it by 2. Right, so the length of rattlesnakes is normally distributed with standard deviation 0.4, given 5% have a length of less. This is a big old question. 5% of the snakes have a length less than 1.7 meters. Find the length of a rattlesnake. So, all right, I'm going to give you guys 3 minutes, not to do anything, just to go through this, read it through, and decipher what that, and then I'll give you guys a bit more time to actually do the question. So to start with, just identify what it wants you to do. Don't worry about doing it for 3 minutes, I say, to just work out what the question is getting at. Could you guys comment what the question is actually asking? So A, B, C, D, what do they actually want? Mike, yeah, it's on there. Any others? What is each bit asking for? Okay, yeah, normal with Z. So we're trying to find mu, so we need to use the Z distribution to find mu. Cool. Part B is normal and binomial. Well spotted, Dan. Yep. So normal because we've got to find this bit with normal. The rest is then binomial because we got at least 6. So that bit there, binomial. Part C and part D hypothesis. Yes, so this is hypothesis test. And part D is, you don't have to do a new test, but it's going to be kind of linking, that's somehow going to link in with what you did already. Yeah, so comment on hypothesis test. Cool. All right, well done, those of you who commented and got some things there. Can you guys give it a go? So what's it worth? 4, 7, ooh, 10, 12 marks. I'll give you guys 10 minutes. I don't want to spend all lecture on this. So 10 minutes. You've already decided what it's about. So let's see how that goes. So 10 minutes starting from now. And please comment your answers when you got them. Yep, looking good so far, you two. Don't know about your part B there, Sam. It's different to what I got. That's what I'll say. Um, oh wait, I might have done that wrong. Yeah, no, you might be right. I doing it on the class whiz and I didn't type things in right. Um, yeah, no, I do agree now. Yeah, Samuel is right there. Regan and Sam, you two are wrong, I'm afraid. If you guys have a look at that again. Yeah, have a check through that, Dan. Check through workings. It's easy to do a sign error in these. So for B, you're going to do an NCD. Just do a standard normal. I don't think so. Not with that far out. You and Sam, it looks like you've done the wrong thing together. Um, all right. So yeah, you do the normal for greater than 2.3. Find the probability, and then use that with a binomial. Remember, the class Wiz only does less than or equal to for binomial. Um, see if that helps. Yeah, Regan's got the right answer to A. Yeah, part B is the one, Regan. Yeah. Two minutes left. Anyone need any help? Yeah, that's it done. I'd normally do like 2 dp, really. Probability is normally given to 4 for normal. Things like mean and standard deviation, 2 decimal places normally suffice. All right, let's go through this. So yeah, some of you guys got most of the way there. Pretty good. Let's get rid of this and do some workings. All right. So first one, 5% have a length less than 1.7. So we're trying to find mu. So if we draw this, 1.7, this is 5%. We know L is a normal with an unknown mean and a sigma of 0.4. So we're going to use the whole z equals x minus mu over sigma. So if we bring up the calculator, we're going to do a standard normal distribution. And we're in tail to the left, area 0.05. This is the last one I did, that's why. Sigma is going to be 0. No, it's not. Sigma is going to be 1. And mu is going to be 0 because we're doing a standardized distribution. Execute. We get z is minus 1.6449. Equals x. X is 1.7 minus mu over 0.4. And if you rearrange all that, you should get mu is, was it 0.5242? I think, unless I've done it in the wrong place. Nope, 2.358. Cool. Everyone right with that so far? Cool. All right. So that's the first bit. Next one. Oh no, I needed that mean. Was it 2.358? So let's write that up here. So L and 2.358 and 0.4 squared. That'll do. We can just about see all that. Okay, part B. 10 are chosen at random. Cool. So straight away, thinking this is binomial. So we've got binomial distribution with x is a binomial number. Well, we've got 10 chosen. And probability we don't know. So we need to work out this probability again. So we need to work out for our binomial the probability that x is at least 6. But to do that, we need to do the normal to find out the probability that any snake has a length greater than 2.3. So we need to do the normal bit here on the calculator, and then whatever we get for this is our probability for our binomial bit. So if we type all that in, it's just a NCP1, NCD even, NCD lower 172, no, greater than 2.3, so lower is going to be 2.3. Upper 1,000, yeah, why not? 1,000-meter long snake, that would be terrifying. Sigma is 0.4 and mu is 2.358. So we get z is 0.5576. So that is our probability for this bit. So let's write that in, 0.5576. And then we can just type this in on a binomial function. So binomial distribution, binom, BCD, lower, it's going to be 6. No, is this right? Yeah, upper, well, how many are we doing? We've got 10 trials, so upper is going to be 10. Number of trials, 10. P success, 0.5576. Nope, 5576. So overall, we get 0.5241. So yeah, Regan 525, that'd be fine with some rounding. 524, yeah. Maybe it should be 524. I don't know if, yeah, you're probably right there anyway. So I'd always give probabilities to 4 decimal places, is what convention normally says. Okay, so now we're on to the hypothesis test part of the question, which I think is new, so it doesn't use any of the stuff we've done before. Right, so last bit. Adult female rattlesnakes are lengths M. So M is now a normal with a mean of 1.9 and a sigma of 0.3. So we got the distribution of sample means. M bar is normal with a mean of 1.9 and 0.3 squared over, how many we got? 20. 20. Okay, so there's our distribution for our female rattlesnake lengths, whatever it is, female rattlesnake lengths. So what we're doing now? Okay, so we need to state some hypotheses. So H0 mean is 1.9. H1, the mean is, are we doing that? Not equal to. So we're doing a two-tailed test, 1.9. Draw my distribution. 5%, so for each tail we're looking at 0.025. Trying to find out what the critical regions are. Yeah, cool. All right, so let's get out the calculator. Invner. Tail, we'll do left first. 0.025. Sigma 0.3 over square root of 20. And mu, what was mu again? 1.9, supposedly. Cool, do that. We get 1.7, 1.769. So critical regions. M is less than 1.769. And the upper region, change the tail. M is more than 2.032. No, 2.031. I cannot round. Anyway, so what's the snake length? So that's part C done. We found our critical region. Part D, the length is 2.09, so that's going to be critical. Sorry, rattlesnakes. So 2.09 is greater than 2.031, therefore critical. Therefore accept H1, and we can say the female rattlesnakes are likely longer, have a mean length should be longer. Cool. Everyone wrote that. What did everyone get? Everyone got slightly different things, did they? 1.0, 1. Yeah, everyone got slightly different things. Joseph and Dan, you did the same thing, whatever you guys did. Did you forget square root 20, maybe? I don't know. Let's have a look. Why not? So if you forgot square root 20, you would have had 0.3 divided by 20. 1.93. That's close to what you got. Yeah, maybe that was some rounding. So don't forget to root the 20. So yeah, me and Sam agree. That's all good. At least someone agrees. Okay, let's get rid of this. How long we got? We got 25 minutes. Cool, it's loads of time. All right, we're going to do another hench question. Is the plan. We can do this one about cats, but I thought we could. I got loads here actually. Look at how much I thought we'd get done. Um, yeah, I think this is the big one. So this was. I mean, this is from the old A level. This would be from years ago. So the marks are probably a bit inflated, but we got 10, 15, 18 mark question. Cool. All right, if I'll give you some tips for it. Let's just have a read through. So a company has a fleet of identical vans. Placed, okay. So X, the variable we're talking about is the number of miles driven before the tires are replaced. X is normal. We've got mean, we've got standard deviation. That's why it's worth so much. Back then you couldn't use calculators. So part A says it's worth 4 marks. You can just type that in and do it in 2 seconds. So yeah, it's definitely not worth 18 marks anymore. 10 vans in the fleet are selected at random. So yeah. Cool. Yeah. Okay. This doesn't sound like it's gonna be too hefty anyway. So let's give it a go. It's 18 mark. I don't think it is. I reckon 10 minutes, and then that gives us a bit of time to go through it and just remind you guys about the assignments. So yeah, if you could all try this one, ignore the marks. They don't mean anything anymore. Yeah, 10 minutes on the clock for this one. Type your answers, and yeah, thank you guys. Can I just double check that Will, Zach, Sam, C, Lottie, Hannah, Carrie, Sam H, not Humphreys, and Isaac are not here because I'm gonna mark you guys absent on the register unless you speak now. Right, now I need to do this to check your answers. So yeah, your answers to part I look pretty good, guys. Oh, Hannah's here. Sorry, Hannah. Anybody else? I'm still missing Will, Zach, Sam, Lottie, Carrie, Sam, Isaac. Yeah, Dan, part B looks good. B is, yeah, normal binomial, but it's easier than the ones we've done so far. So read the question carefully, and you'll find it's a little bit easier than usual. Part B. Yep, that's right, Sam. And Regan, yes, good job so far. Critical value. Mine was different than that. Yeah, that's better done. Cool. All right, that wasn't so bad actually, was it? No. Okay, let's do this one then. Cool. Right, so yeah, this wasn't too hard at all, to be honest. It looks a lot worse than it claims. You see how much marks used to be worth, but back then they didn't have calculators, so kind of fair. Right, so we got x normal 27500 mean 4000. So bring up the old graphical and distribution normal. I will find p so we're using NCD. Great then. So lower is 25,000. Upper 6 billion. Sigma 4,000 and 27500. Cool. So you get 0.73. There we go. Next bit. So binomial now. So we got what should we call it? Z? No, Y is a binomial. 10 selected, and if you look, it's the same question. So that's nice of them, 0.734, so you don't need to do any more work there. And we want to find the probability x equals 7, which we haven't done in a while, so that's good. So we can use a binomial percentage distribution because it's equal to. So binomial BPD, and put it all in. So x, we want 7. Trials, we want 10. Oops, no, don't do that. And p is 0.734. Cool, now we're ready to go. So we should get 0.259. There we go. Okay, tires. So now we got a inverse normal. So we're told the tires on 90% of vans will last for longer than K. So K is down here. This is 0.99. We're trying to find K. So I think I did less than on my calculator. I think I was doing on the class widths. NCD. It's up to you guys which way you go around. Oh, inverse even. Invna. Normal. Invna. And yeah, so tail to the right, or you can do tail to the left, and I wouldn't do 1%, but yeah, 0.99. Sigma is 0.734. Mu is 10. And there we go. So K is 8.2. Does that make any sense? No, I've done something wrong here. What have I done? Mu is 4,000. I'm looking at the wrong question. Sorry, sigma is 4,000. Mu is 27,500. Cool. 18194. Yep. 0.6, as you all said. Good. Okay, last bit, hypothesis test. So null and alternate. So null mu equals 27500. We're testing if it's better. So h1 mu is better than 27500. Okay, cool. That's it. There's free marks for that. What were they thinking? Okay, for 15 vans, mean is that carrot test at 5% level. So we're going 5%. Let's find our critical region with 15. So the sample means is going to be x bar and 27500, and then we've got sigma 4000 squared over 15. So put that all into the calc. We got tail to the right 0.05, sigma 4000 over 15, root 15. Bish bash bosh, there we go, 29198.8. Why not? Okay, so our tires were 28630. We're less than that, we're not critical, so our tires are no better. So carrot test at 5% level. So let's do a different color there. 28630 is not critical. Therefore, tires are no better. Cool. There we go. So yeah, nice. Hopefully that today has kind of cemented those topics in. Go over them. There's the tiniest bit ever left of stats, and it's easy. So we got one easy week left. If you found stats better in second year, go over conditional probability. People do find that difficult. Go back and just relearn the first year stats. I'm doing videos at the moment, and then you've got stats down. So yeah, and I also do the mechanics videos as well. So over Easter, do some revision, start making your way through some past papers. I know you guys don't have an exam, but you still need to know the stuff. So keep revising, work your way through past papers. Let me know if I can be of any assistance, because isolation ain't got much to do. Yeah, and get those assignments and skills checks done. If you could, I know ideally just plow your way through them, work your way through that over Easter, finish the course, have all the assignments done. That'd be a really good place to be in. Cool. Anyone got any questions? I know we've got 5 minutes left, but we aren't going to get through another question in 5 minutes. If you guys do want to do any more practice on this, I will slowly there you go. Or you can screenshot each of these if you want a few more questions. So slowly cycle through it. So take a picture of this one. You can pause it, rewind it. There's this one. And if you want the answer to any of these, let me know and I'll just do them. Yeah, I'll be going through mechanics tests. They're sat on the floor here. So I'll pick a day at some point, let you all know when. If you're all free that day, we'll do like little phone chats, and but yeah, I'll basically just show you what you did wrong and talk to you about what you did. It'll probably be in the second week of Easter, to give me a week to relax, because it's a lot of work doing these lectures. Yeah, so get those done, and then we'll sit down and I'll just flick through each one, talking you through what's wrong. That'll be just as good as anything else. Cool. And that's it. Cool. Anyone got any other questions or anything? I've shown you all how to do the Moodle stuff, how to access the assignments and the skills checks, so please do those. Yeah, and revise. So after Easter, yeah, 1 week on our correlation testing, and then we'll start doing past papers. I think I'll just film myself doing past papers. Yeah, and then you guys can hopefully pick stuff up along the way. Cool. Right, cheers guys. I will speak to you. I'll be 2 weeks until we have another next lecture, but I will drop you emails about when we could do one-to-ones for mechanics test handbacks. Yeah, check out some other videos if you want to revise your first year stats or your mechanics because they're all up. All right, cheers guys. Bye.